Welcome to the satellite communication course. Today we start with the next model that is about a propagation effects. So in that propagation effects, we will learn here what will be the propagation effects occurs while transmitting the signal from the Earth station to the satellite. So we say that we have a satellite and for each and every satellite there are the various antennas and we are propagating the signal from the Earth station to the satellite here. Now, when we are communicating to the satellite through the Earth station, that will be your uplink, as well as we are communicating from the satellite to the Earth station, that will be a downlink here. This one will be a uplink, and this one will be a downlink. Now, in this region, when we are propagating the signal or we are transmitting the signal from the Earth station to the satellite, so in that case, in this particular region, there is some we can say this one is nothing but a atmospheric region. So now, today we are learning here what will be the propagation effects occur when we are transmitting the signal from the Earth station or when we are transmitting the signal from the satellite to the Earth station. So we learn here a transmission mechanism, what are the problem occurs while transmitting the signal, and transmitting the signal means what? We are transmitting that electromagnetic waves, that is in terms of a gigahertz there. So when we transmit the signal in a free space here, because this one is nothing but a free space region, you see a signal transmitting from this free space region to the satellite here. And then what happened to your signal when we transmitting, that will be for the uplink, and what will happen to the downlink here, that we are learning in this model. So now we will learn what are the effects occur on this particular signal transmitting. So generally we say that when we transmit some signal, so then they have the near the earth station, it has some particular atmospheric conditions are different, okay, near the earth station. So we learn here what are the various atmospheric conditions. We learn that atmospheric condition, and due to this various atmospheric condition, what happened to your signal transmission there, that we are learning. Now what happened means what? Due to the atmospheric condition, what are the various losses occurs in a transmitting signal. Now we say that there are the various satellite. We say that low Earth orbit satellite, medium Earth orbit satellite, and a geo satellite. Now in this case, if supposed to be it is a low Earth orbit satellite, what will happen? What atmospheric effect occur on this particular satellite? So we talk about the what are the various losses when we consider the different height of the satellite there, and that losses means what? Signal level get degraded or signal get absorbed in this particular region. This one is the atmospheric region, that is in this particular atmospheric region when we transmit the signal, then atmosphere has some various elements, and that elements are nothing but some ionized gases, ionization, some gases effects occur on the signal. So due to that atmosphere, when we transmit the signal from the earth station to the satellite, so atmospheric effect occur on the signal there. So that atmospheric effects means what? That signal get degraded or our signal strength get reduced. Means what are the effect occur? The strength of the signal reduces here. Strength of the signal reduces because of that atmospheric effect, and that's why we say that uh, that signal reduces means what? There will be attenuation or there will be absorption in that particular region, or there may be a changes in the phase. There may be a changes in the phases of the signal, or because when we transmit the signal or receive the signal, that that signal may degrade in terms of a phases also. Okay, that phase change occur, and these losses are due to the what will be that losses are due to the atmospheric absorption and the attenuation. These losses in this particular region because of that atmospheric absorption, or we can say because of the attenuation there. Or again, that losses will be what we say here, atmospheric absorption and attenuation. Okay, we can say that we have the losses, atmospheric attenuation here. Then again, we have the losses because of a cloud attenuation. We have the losses because of that cloud attenuation there, or we have the losses of the signal. We can say that signal degradation occurs, strength of the signal reduces because or phases reduces because of that atmospheric absorption and attenuation, because of a cloud attenuation, or we can say that because of that rain attenuation, because of a rain attenuation there. Then we say that a tropospheric, and we can say that a ionospheric, tropospheric and ionospheric conditions changes, or we can say that a tropospheric or a ionospheric scintillation, or we can say that there may be changes in the position of the signal there. So that's why we can say that it's about a Faraday rotation that belongs to, we can say that it's a position changes of the signal there. And another one is about, we can say that rain and ice crystal depolarization. Now these are about the mainly effect why your signal degrades. Signal degrades because of what? Absorption and attenuation in the atmosphere, because of a cloud attenuation, because of a rain attenuation. Okay, then because of a tropospheric and ionospheric scintillation, means that layer, that is tropospheric layer or ionospheric layer above the Earth surface. Okay, that's why that changes in the signal strength or a signal reduce there. Because of that Faraday rotation, signal reduces. Because of the train and ice crystal depolarization, your signal reduces there, or their phase changes. Okay, we are talking about the signal reduces as well as there is the changes in the phase because of all these factors here. Now we consider here that when we consider that absorptions or a phase changes occur, means we can say that signal reduction takes place in this particular region. That is because of the what atmospheric condition. Now we consider here why this occur, why this why this signal strength reduces. Okay, that we are learning. So we are learning here in the model 3 what are the propagation effects, and that propagation effects occurs on the signal, transmitting signal as well as the receiving signal, and that whatever the signal strength reduces or changes in the variation in the signal, that is again depending upon that frequency. Everything is depending upon the frequency. So generally we say that radio waves we have, if we have the radio waves below a 30 megahertz, that will get absorbed, and pre pre signal communication takes place if our signal above the 3 gigahertz, then atmospheric effect will be reduced. But if you consider that the satellite, we have a L band, C band, and S band, that operating frequency is different. So below 3 gigahertz, Then what happened below 3 when we transmit the signal with a below 3 gigahertz of signal frequency? So then ionospheric layer will come in a picture. So below 3 gigahertz of a signal, so ionospheric signal may be act as a reflector or maybe act as a refractor there. So we'll learn here. So what will happen to the ionospheric layer at this particular frequency there. So effect of the atmosphere based on the frequency that we will learn. And that losses we say that it is not only for the uplink, it can be for the downlink too. So means we say that while designing the satellite link for the uplink or a downlink, so we should know that what will be the power requirement, because there may be losses, that atmospheric losses at that some particular frequency. So because of that losses, signal reduces, signal strength reduces. So because of that signal strength reduces, we need to consider at the time of satellite link design. So what level we require for the transmission. So simple example, as I told you earlier, so you people have the dish at a home, but due to the rain or due to the cloud, so receiver means dish TV at a receiver at home, that will be act as a receiver. So that dish is not able to receive the signal from the satellite because of that cloud and a rain. And that is nothing but the attenuation due to the cloud and rain at that particular frequency. But if there is no cloud and rain, so signal get received, signal will be clearly received by the dish TV, dish. But due to the rain or a cloud, signal get affected. So means your signal is whatever the signal frequency we are using. So attenuation is depending upon that frequency. So operating frequency. So that's why we should know that your satellite will work for the whether low Earth orbit, medium Earth orbit, or a geo satellite. Or we can say that all the satellite work at that what particular frequency there, operating frequency bandwidth. So that losses that will be due to the whatever the frequency operating. At what your satellite signal operate at what particular frequency. So that losses will be more or less. Okay. So we learn that what particular frequency your losses will be more there. And then again we say that atmospheric condition changes in a day or a night. So you can say that atmospheric condition is changes. That atmospheric condition is a time varying condition. Okay, this will be a time varying one. Time varying atmosphere. Okay, so atmospheric conditions are time varying. So that's why we consider that at what particular period of a time your signal can be transmitted, or we can say that so for the uplink atmospheric condition will be different because the frequency is different. For the downlink, atmospheric condition different because the downlink frequency is different. And again, it is a time varying or a time dependent. So while considering the a satellite link, we need to consider that uplink frequency signal. So system margin or that particular loss is to be considered for the satellite link design. Okay. So in a satellite link, we say that a power received that will be is equal to what will be the EIRP plus we can consider that what will be the that sorry we consider that what will be the minus LP here. That is about a path loss we consider. Again we need to consider that what will be the here again one more factor, that is about a gain of a receiving antenna, and what will be the system margin. Now this system margin is nothing but what? At a daytime or a night time, what will be the power to be transmitting from the earth station or from the satellite? So that transmitting power we can vary so that a received power we are getting. So we consider that a system margin there. Okay, so that much will be the system margin. So we can vary your transmitting power based on the day or night because that ionospheric layer will changes with respect to the day and night. So now we'll learn here what will be the ionospheric layers and all. And again, these losses, that atmospheric losses, that will be changes based on the day or night as well as the what will be the receiving antenna we are using because that condition changes, atmospheric condition changes, so your antenna performance will degrade. Okay, that's why that is about a factor we say that is about a noise factors and all. Now we consider here what are the various effects on the signal there while propagating while propagating the signals here. So we consider first a what will be the ionospheric effect. Now generally a ionospheric layer, if you consider that, or a ionosphere region, that will be approximately from the Earth's surface, that is from the 15,000 to the 2,050 kilometer to 2,000 kilometer there. And that ionospheric region consists of the ionized gas or ionized molecule. Okay, that will be ionized gas or ionized molecule there. And that ionized gas or ionized molecule that will be based on the what will be the solar radiation. That solar radiation from the that will be in the band of what we can say X-ray band or a U band. Okay, we can consider that, or we can say that ultraviolet frequency band, UV band. Okay, now so that ionized gas or ionized molecules, they contains a free electrons and a positive electron. Consider that electrons and a positive ions. Okay, these are about the ionospheric molecules, or you can say that is about it that ionized gas, whichever the ionized gas we have, they contain the free electrons and a free positive ion. And all these free electrons and positive ion, they are electrically neutral. But in the when we consider that in a lower atmospheric region, so we'll see that what will be the ionospheric regions and all. So I'll draw the diagram. Earth now, this one we say the Earth. Then we have the okay, that is about a one is the layer we have. Okay, it's about the layer. So this is about a D layer. This one is about the E layer here. Okay, so I'm trying to draw circular fashion here. Okay, This one is about, we say, we have the earth, and this particular region, that is a day region, and we have a night here. Miss D and E layer, if you see that this one is about a D layer and E layer, that will be merged in a night. And we have the F1 and F2. This one is about F1 and this one is about F2. So this is about F1 and F2 layer that will be merged at a night. But in a day, it is separated. Here you can see that this one is about a F1 and F2 that will be merged at a night here. So similarly, we have the D layer and E layer that will be merged in a night. So that's why we say that the atmospheric condition is a time varying. Okay, atmospheric condition is a time varying because of that solar radiation. So we say that the ionized gas molecules, okay, so that they have the free electrons and positive ions. Okay, so that it changes because of the day and night. Okay, so we'll come to that particular point. So what will be the ionospheric layers and their attitude? We'll learn. So if you consider that a layer, that will be a D, and that will be that attitude here, and their electron density at day here, and electron density at night. So we consider that one by one. So if it is a D layer, so that D layer is about from the 50 to 90 kilometer of a length, and that will be from 10 to the power 9 per meter cube in 75 to 80 kilometer of a range. Okay, that is about in a day. But in a night, it will be very low. That electron density, that will be low there at a night. But it has the electron density that will be 10 raised to power 9 meter per cube. Okay, meter cube in a 75 to 80 kilometer of a range. Now in the E layer, so if you see that we have the region of what 90 to 140 kilometer, and that they have the electron density 10 to the 11 by meter cube, and that will be in what we have the 100, we say that 100 to 110 kilometer of a range here. And in the night, it will be drops to 10 to the power 9. Okay, that will be the night here. But in the case of a F1 layer, that altitude, it occurs at the altitude of what 200 to 250 kilometer, and that density, that will be varies from 1.5 into 10 to the power 11 meter cube to 4 into 10 to the power 11 per meter cube, with minimum minimum and a maximum solar cycle. Everything is depending upon that the solar cycle, that is in a day. And at a night, the F1 layer, at the night, the F1 layer disappears. Okay, F1 layer, that is merged. So that's why you can say it is about a merged here, we say. But it is, it disappears. But in the case of a night and a day, okay, so that variation occurs. So day here it has the electron density, but night it disappears. And then F2 here 300 to 400 kilometer, and that will be from 5 into 10 to the power 11 per meter cube. That is the electron density. And in the day, night, that is 4 into 10 to the power 11 meter per meter cube. That is about the electron density. Now we say here, so that ionized gas contains, we say that is about a free electrons and a positive ion there, okay, that we are saying. But in the case of a lower atmospheric condition, okay, in the lower atmosphere, so that what happened for this particular ion molecules, some small fraction of that oxygen and nitrogen molecules that will be ionized here, and because of that they leaving large number of a neutral molecules, because we say that they have a few free electrons and positive ions, but both are that we can say electrically neutral one. But when we transmit the signal, or when we pass a signal through this particular region, so what happened, that ionized region of the atmosphere, okay, whichever we can say that is about the ionized region of that atmosphere, that is about a layer, this all these layers we see, they interact with that particular free electrons present. Okay, so when we can say that whenever we can transmit the signal, or we can say that when a radio waves passes through that ionized region of the atmosphere, they interact with the free electrons present in this particular region. Now that because of that interaction of that free electrons, so what happened, because of that free electron, sorry, different slide here, okay, when they are interacted, interaction of a free electrons, when our signal will interact, or we can say that when our signal or a radio waves propagating through this that ionized region of the atmosphere, they interact with the free electron, means interaction of a free electron takes place, and because of that interaction of the free electron, they introduces a group delay. They introduces a group delay. They introduces, we can say that, a polarization rotation, then attenuation, attenuation due to gases, then we can say that a cloud, and or we can say that it's attenuation due to the, we can say that is about a glasses, then cloud, and we can say that is about a rain. Attenuation takes place because of this three factor here, or we can say that a depolarization, depolarization due to rain and ice. Okay, so means we can say that again there will be change in the angle of arrival, that is when we can say that when we transmit the signal, or we can say that satellite transmit the signal to the earth station, then angle of arrival of that particular radio waves or a signal will changes there, and all these effects occur, and all these effects that will be based on the, all these effects that are based on the frequency. So that's why we should know that at what will be your transmitting signal frequency. So generally we say that when we transmit the signal that will be of a below 30 megahertz, so what happen? So that signal will be what? That will be reflecting or absorbing. If you transmit the signal, that will be below 30 mega. So that's why then we say that a satellite communication cannot be take place at the 30 mega below 30 megahertz of a frequency. And then again we say that above 3 gigahertz of signal frequency, that ionospheric layer will be transparent. That you can say that above 3 gigahertz, so we can say that a ionospheric layer that will be a transparent to the your signal, or you can say that is about a above 3 gigahertz frequency. That ionospheric layer will be a transparent. So we can communicate or we can transmit the signal. Transmission of the signal takes place that will be above a 3 gigahertz of frequency. But if we consider that below 3 gigahertz, but below 3 gigahertz and above 30 megahertz of frequency. So in that case, what happened? Below 3 gigahertz of a signal, that will be what? Eh, that will be changes because of that ionospheric scintillation, and we can say there is about a multipath fading there. Or that ionization causes that will be changes in the polarizations or attenuations or depolarization due to the rain or angle of arrival will be changes. So means we say that a density of free electrons, okay, that is about these are about a density free electrons, and that density of this particular free electrons that will be changes with a day or a night. So that's why we can say that free electrons varies or their density will be changes at the in the day or a night, because ionization will be occur when we have the solar radiation. Okay, that ionization effect occur because of that a solar radiation. Means we say that ionization is caused by the solar radiation, and due to that solar radiation, so that free electron density will be changes or electron density will be changes at the day or a night. So absorption is takes place here of the particular signal, because absorption of a solar radiation in that particular region takes place. So that's why so electron density will be different at the different timing there. So that's why that we say that there are the different layers, and those different layers they have the different attitude. At different attitude we have the different or we have the variation in the density occur. So this particular table, if you see that, that will just explain that ionospheric layers, and that ionospheric layers what will happen to the day or night. So satellite communication, if you consider that, that is to be done above 3 gigahertz, or if you consider that below 3 gigahertz of a frequency, then your signal get attenuated. So now we come to the topic that will be a atmospheric attenuation and sorry the different page here, atmospheric absorption and rain attenuation. Now, what will happen to the signal? We say that when our electromagnetic waves are propagating, so then attenuation will be occur or absorption of the signal will occur, and that absorption or attenuation that will be depending upon that frequency. So we say that is about a frequency dependent. Okay, so that attenuation or absorption that is again depending upon the frequency. So that is a absorption or attenuation. That is nothing but what we have that free electron, and that these free electron they have the molecules, or we can say that we we can consider that in the particular day or a night we say that is about a their electron density changes, or this particular free electrons they collide with a particular molecules, or they collide with the atoms. So we say that there will be a collision of what? There will be a collision of what? A free electrons with a neutral atoms and a molecules. Means your wave is propagating through this that particular atmospheric region, and because of that collision, okay, because of that collision of that electron, so what happened because of that collision? So that wave will get attenuated. So we say that wave is propagating through the space here because of that collision of a free electrons with neutral atoms and a molecule. Your wave will get attenuated there, and that attenuation is occur based on this particular frequency. So we can say that interaction of that particular free electrons occur at some particular frequencies, and at that particular some frequencies we say that there will be a loss, and that loss will be high at a particular frequency. That loss will be had high at a frequency. So we should know that at what particular frequency that attenuation will be high. So we can consider here that a graph, if you see that we have the graph of what we can say it is about a frequency, and if we consider the attenuation here. Now that is about the attenuation we have, and this one is about a frequency. That will be frequency from the 10 to 100 gigahertz, or it is in the gigahertz. That will be 40, 50, 60. Now at that particular frequency here, if you see here that particular graph, now you can check that earth station they have some particular elevation suppose. So we have the attenuation occur if for the satellite, here you can say that when we transmit the signal, when we transmit the signal, attenuation of the signal occurs or at that particular reception. So what will be the elevation angle? What will be the angle of elevation? So according to that angle of elevation, so arrival of a signal, or we can say that transmitting of the signal, that we transmit the signal in the space here. So according to the elevation angle, so your attenuation will be changes. Means we say here a signal have the losses at a frequency, but it is depending upon that elevation. So now if you consider the graph here, so different elevations angles at a particular location, and in that case, if you consider that there may be a at some particular frequencies there may be a lot of loss. So generally, this may be a attenuation at that particular frequency. Okay, if you are able to see that this is about the frequencies in gigahertz, this will be the attenuation here. So this one is the attenuation occurs at that elevation angle. So right now I'm just saying that this one is about the elevation angle, below is about a 30 degree now. This one is about the elevation angle. I just draw first, then I'll type right that elevation angles and all. This one is about the elevation angles we say here, and this is nothing but the attenuation of the signal frequency. Now I'll write here this is about first line is about a 30 degree. We have the elevations at a 30 degree. Sorry, the first line this color is nothing but a 30 degree. I'm just writing here. This blue is nothing but what we can say it is about 20 degree. Sorry, blue is about a 10 degree here, and this black is about a 20 degree here, and then red is about a 5 degree. All these are the degrees. Now that when we vary the frequencies, attenuation is from what we can say it is from the 5, 10, 20. That all this attenuation is up to we can say that is about a 40 here. Okay, 10, 15, likewise up to a 50, 14 here. So these are they have the attenuation, but in this particular band of frequencies, if you see that the attenuation, that absorptions and attenuation is less here. Okay, so 60 gigahertz or this one particular gigahertz the frequency, that attenuation is low. So from this we say that when we transmit the signal from the earth station here, so based on the elevation angle, your attenuation will be it changes. Why it is changes? Because that a collision of a free electrons with the neutral atoms occur. So that's why that attenuation changes. Now at a different elevations angle, or you can say that a different locations, so that attenuation will be changes. So means if you consider that at this particular frequency range here, means resonance, this is about nothing but here some particular peak is occur, and that peak is occur at the 22.5 gigahertz. This is occur at a 22.5 gigahertz. That will be for the water vapor. And if you consider that at this particular 60 gigahertz, okay, at the particular 60 gigahertz, it has some particular O2 oxygen. So that's why that attenuation, if you consider at that particular frequency, is low. So we consider here the zenith atmospheric condition or a zenith atmospheric attenuation based on the dry air and a water vapor with a density at a 7.5 gigahertz. We continue there. So in that case, we consider there the zenith attenuation at this particular place, and here we have the a density, or we supposed to be consider that at what particular values of this attenuation. So if you draw the graph there, so in that case, this will be the attenuation occur with a particular peak values. We say that it's about a 10, then we can say it is about 100 here. So that is about the attenuation. And in that case, attenuation is about, we can say it is about a a 10 to the minus 1, then 10 to the 1, then we have a 10 to the 2 here. That is about the attenuation. So that is about the zenith atmospheric attenuation condition. Okay. So that is about attenuation for the dry air and a water vapor with a density of a 7.5 gram per meter cube. That is about the attenuation. Now next we consider that a cloud attenuation. We consider here cloud attenuation. So what happened? A cloud attenuation occur at the tropospheric region or a troposphere there. Generally we say that clouds are present at a troposphere. Okay.